In this demonstration, we're going to be talking about calculating current flow through a DC parallel circuit. The reference for a DC series circuit is the current, and it is unchanging at all points, or the current flow is the same at all points in a DC series circuit. Well, in a parallel circuit, voltage is your reference, and it's unchanging at all points. If you were to measure from the two different points at either R1 or R2, you would be able to measure the 32 volts across those resistors. So that becomes your reference. And in the parallel circuit, you have a division of current because you have branches. Well, in order to calculate the current flow through the individual branches and the division of current, once again, you're going to use Ohm's law to do that. So looking at what we have done in the past, cover up what it is in the Ohm's law circle that you need to calculate, which in this case is current, and use what remains. So we cover up the I, and we're going to use the two remaining values, which is E and R, in order to calculate the current flow. So the first one, we will calculate the current flow through R1 using Ohm's law. So we're going to be using our voltage, which once again is an unchanging constant, or the reference in your parallel circuit, divided by the value of R1, or 32 volts, divided by 18 ohms. And that will give you a current flow through resistor R1 of 1.778 amps. Now, I wanted to point out that carrying your answer a couple points beyond the decimal points, 2 or 3 points, will help you in your calculations, because if you go too far, you run the risk of maybe punching something into your calculator incorrectly. But if you don't go far enough, then your answers may not be correct. We'll get to that when we finish out the totals. So we can go ahead and calculate the current flow through R2 also the same way, just going to be using different values. Same formula, so the voltage divided by the value of R2, or 32 volts divided by 12 ohms of resistance on R2, will give us a current flow of 2.667 amps of current flow through R2. Now, just like the voltage drops across the resistors in a series circuit, there's a law or a rule that applies to current flow in a parallel circuit. The division of current on the individual branches in a parallel circuit are equal to the total current flow in the circuit. And you can prove this a couple of different ways. Now, you can go ahead and use all of your totals. We calculated the total resistance, or the total opposition to current flow earlier, and we have the source voltage. So if we wanted to calculate total current flow using Ohm's law, we can definitely do that. And you're just going to be using all of your totals. So the I total is what we're looking for, is going to be the E total divided by your R total, or your total opposition to current flow, or 32 volts, which is our source voltage, divided by 7.2 ohms. Now, that answer for your I total is 4.44 amps. So now we can prove that by going back up and taking a look at the other two. There's another way to write out or to calculate the I total. And in this case, we only have two resistors, but the current flow, or the total current flow, can be calculated by adding together all the individual current flows. So the I total, in this case, could also be calculated by adding together 1.778 amps plus the 2.667 amps of current flow through R2, which will give us a total current flow, if we punch that into the calculator or just add them together, of 4.44 0.445 amps. So we've proven that our calculations are correct in this case. Now, a couple of other things can be said about the current flow in a parallel circuit. Do a comparison of the current flow from R1 to R2. So the current flow through R1 is 1.778 amps, and the current flow through R2 is 2.667 amps. And one thing that you can see right off the bat is that you have 12 ohms of resistance here and 18 ohms of resistance here, while the one with the lower opposition to current flow has the greater current flow through that branch, or the one with higher resistance or higher opposition to current flow allows less current to flow through it.